Good evening, young astronomers. Tonight we're going to talk about the patterns in the sky. This is the astronomy that human beings have been doing for thousands and thousands of years. This is astronomy that you can do, that we are going to do in this semester. I want you to start noticing the objects in our sky. Notice how they change. They're going to change during the course of a night. They're going to change as we go along in the semester. You're going to see that some of the objects in our sky are going to be in different positions. And that's what we're going to learn about tonight, why the sky looks differently. You all know, I talk about how, when I talk about things moving across the sky, I'm not talking about where you can just sit there and watch them. I mean, in principle, you could. You'd have to be the most patient person in the world. And even then, you probably wouldn't be able to perceive it. But you all know if you go out at a different time during the day, the sun will be in a different position in the sky. That's what I'm talking about. Maybe marching across the sky maybe is a better way. When I say things move across the sky, they think we're talking about airplanes or birds, but it's not that quickly. And we, in our first discussion question, we figured this out. I mean, if you didn't, maybe you figured it out without knowing it. But the sun's position in our sky is not because the sun is moving through our atmosphere, which is the obvious. If you came into this world and hadn't learned anything, think of ancient man trying to figure out what this object in the sky was. It looks like it's something flying across our sky, not fast enough for us to see it, but slowly moving. I mean, even in our atmosphere, you can't tell how far it is. One of the interesting things we have to wrap our minds up is we have no depth perception, especially with these objects. These objects, the sun, the moon, are unimaginably large. They're very, very far away, but if you didn't know they were that large, they could look like, relatively tiny. I mean, they look, the Goodyear blimp sometimes looks bigger than the sun and the moon does. So, and remember, we don't feel like we're moving, so our instincts tell us that they're slowly moving, across our sky. But what's really happening is that they are very huge. They are very, very far away. And while they are moving, that's not what we notice. We talked last week, one of the main principles we need to understand is that the further away something is, the smaller it looks, and it's going to look, if it's a light or a flame, for instance, it's going to not be as bright. The other thing we need to get in that concept tonight is that we also can't tell that it's moving. The sun we're going to learn, it's moving at incredible speed. It's orbiting around the Milky Way galaxy. But that's not what we're noticing. And for one reason we're being dragged along with it. But even if we weren't being dragged with it, it is so very, very far away from us, 93 million miles away, that we couldn't tell if it was moving. Imagine the airplanes as you see them, especially the ones way up in the sky. They don't look like they're moving very fast at all, right? They're moving hundreds of miles an hour. Those planes, especially when they're at that height, they're moving hundreds of miles an hour, 500 miles an hour, but they look like they're barely moving because they're so far away. If that plane was right above your head, it's zooming right over. You can tell how fast it's going. But it's way up in our sky, you can't tell how fast it's moving. So this motion that we see, the sun and the moon rising in the east, setting in the west, they both do, by the way, not just the sun. That all has to do with the rotation of the Earth. Here's our little animation. Watch this. Watch this. It's on our Canvas page. The Earth orbits around the sun like this. The moon actually orbits the sun in that orbit. So everything is in motion here. This tilt, we're going to learn, is responsible for the seasons. The relative positions we're going to learn of the Earth, Moon, and Sun are responsible for the phases of the Moon and the eclipses. The eclipse that I hope you all at least made an attempt to look at it at some part of the eclipse the other night. We're going to learn the science of that right now. That animation that you're going to watch, nothing is correct to scale. The sun is much bigger than that. Even the relative sizes of I think the relative sizes of that's about right. The relative sizes of the Earth and the Moon are correct, but the distance isn't for any of these objects, and the size of the sun is much larger than this. If you haven't done it yet, you will learn in our scale of the universe virtual lab that the sun is actually bigger than twice as big as this orbit. This is the relative sizes of the moon and the Earth with the space in between them. And the sun is actually, the radius of the sun is actually outside of the orbit of the moon. Just to give you an idea how gigantic the sun is. And what that means for us tonight is that we just think of the light from the sun that hits both the Earth and the moon. It's like a giant wall of light that's coming at us. It's not even like the light from a light bulb that comes off in kind of a ray pattern, a circular pattern. The sun is so large and so far away that the light basically comes at us in straight lines. And we need to understand that to understand both the seasons and the phases of the moon. Watch these videos we have an actual time lapse of the moon, of the Earth rotation, and a whole year of the Earth rotating that was taken by a satellite, million miles away. It's pretty spectacular. Make sure you watch that video. So that axis, let's put some numbers on that axis. That axis is tilted 23 degrees with respect to the orbit of the sun around, the Earth around the sun. And it's actually moving, it rotates 1,000 miles per hour. It actually rotates west to east, because remember, when we see things look like they're going in the opposite direction because they're still and we're moving. The sun and the moon rises in the east and sets in the west because we're spinning from west to east. Think of driving in your car and the stop signs look like they're coming towards you. They're not moving, but they look like they're moving in the opposite direction of your motion. That tilt, as the Earth goes around the sun, does not change. Remember, it takes us a year to go around the sun. And we're going 67,000 miles per hour. That'll give you an idea how far away we are from the sun. As I said, the moon does exactly the same thing, rises. You may not know this. You're used to the sun, but because we're, well, maybe I don't know. Maybe you spend more time outside during the night. The moon does the same thing. It marches across our night sky with the same motion as the sun does. The orbit of the moon is pretty interesting. It's in what's called a synchronous orbit. So we can see this on this plot. It takes not 27 days, not 30 days to go around. It takes 27 days. The 30 days that we base our calendar off of is based on the time between the phases of the moon, the time between the new moons. It's close to being the orbit, but it's not exactly the same, and we'll understand why in a minute. Before we do that, we want to talk about how it's in a synchronous orbit. The force of gravity between these objects is incredibly, they're both incredibly large, and they're both incredibly massive, and they're close together. So it actually slows, as they orbit, it slowed them down. Both the Earth and the moon are actually much closer to one another than they are now, and they're moving much faster. But that we call it being tidally locked, and gravity is it's kind of like a lock grip, and it is the same force that causes the ocean tides. It's got a grip on the moon, and so the moon actually orbits the Earth once every 27 days, and instead of spinning on its axis like the Earth every 24 hours, it makes one completion in that exact same 27 days. And look at this slide more carefully on the PDF. You'll see that the face of the moon is almost always the same face it's facing us. It's a little bit different. If the orbit was actually a perfect circle, then we would always see exactly the same face. But we effectively see the same face right now. That's called being tidally locked. It's also called being in a synchronous orbit. And many moons are like that. Turns out that many of those exoplanets are so close to their stars that they're tidally locked. We'll find this really cool, many exoplanets have a really hot side and a really cold side, and then a middle side that's just right. Here's another image of the moon and the Earth kind of together. You're going to see that they look very different. You also may notice this is from that very same satellite that's 1 million miles away. That the far side of the moon looks a lot different than what we see from Earth. And we're going to learn in a couple of chapters, in a couple of weeks, why that is. The far side of the moon is actually quite different than the near side of the moon. Not just in the way it looks. The crust is actually, oh, here we go. The crust is actually much thicker. Don't worry about the color. That's just the exposure. But you can see the far side of the moon is missing these dark areas. And that's not because of the light. These dark areas on the moon are actually lava beds. Used to be vast seas of molten lava that have solidified. They're actually called mare. It's Italian for ocean. Galileo was the first person to observe these. Thought they were actually oceans on the surface of the moon. The far side of the moon doesn't have that. These things are actually caused by impact craters breaking through the crust and the molten rock underneath the crust actually coming to the surface. The crust was too thick on the far side for that to happen. So we've talked about all this in our last chapters. Let's talk about how we specify objects. Part of your work this semester is going to be, or quarter is going to be, to keep a journal on the moon, and you'll be able to do some extra credit and some other assignments where you're going to have to sketch or photograph. But beyond that, you need to tell us what you're looking at and where you're looking at it at. And so we have a coordinate system. Well, part of that coordinate system you're used to, north, south, east, and west, to specify what direction you're looking at. We'll tell you that. If there's some directions on some apps that you can install on your phone that will actually tell you what direction you're looking at, for those of you who have poor senses of direction. But that app will also actually tell you, you can actually point it at an object in the sky and it'll tell you what you're looking at. Pretty obvious that you're looking at a moon, but later on we're going to point it at what you would think is a star, which is actually turns out to be a planet. And so we will, it'll tell you that, it'll tell you the altitude, it'll tell you all sorts of things. The altitude is really just how high it up is in the sky, but we're not going to do altitude in thousands of feet like you think on an airplane. We're going to talk about the angle, kind of the angle with respect to the horizon, kind of the angle that your head is tilted up and down. But remember, you can't actually tilt your head 90 degrees up. 90 degrees would correspond to you looking, laying down on the grass and looking up, which I highly recommend. It's the best way to actually look at objects in the sky, is to lay down on a blanket and look up at them. But if you're standing up, you can specify kind of the angle with respect to um, the horizon. The horizon is the farthest you can see without any obstruction, no trees. The tree tops are at about an elevation of about 18 degrees. For those of you who saw the moon, I think in LA it was about 25 or 30 degrees. One of the things we want to keep in mind is the two different hemispheres of the Earth actually have we have different skies because we cannot see through the Earth. And the way that the Earth is rotating around the sun and spinning, that constant 23-degree tilt means that there's parts of the sky down here that we'll never see. There's parts of the sky up here that the people in the southern hemisphere never see. The only place on this Earth where you can see every part of the sky is on the equator, because you can't see through the Earth. But on the equator, you can't see it all in one night. But if you wait a year, you can be on the other side and you can see the stars that you missed over there. The stars, they don't. It's a little bit more complicated than rising in the east and setting in the west because they're so much further away. They appear to kind of rotate throughout our sky, except for one. You notice there's a bright light here in the center. Well, first of all, let me explain what this picture is. Pardon me. This is if you left your camera open all night long. I assume you all know what exposure is. I have to explain that to many of my other students, but as you being film students, I assume you understand exposure. If not, there's a setting on your recording device, your camera, or the camera that allows it to doesn't refresh. Your eyes actually refresh once every nanosecond, once every thousands of times a second. It's forgetting what it actually saw. That's great if you're running from a cheetah. You want to see where it is, but it's not so good at looking for dim objects. But your camera, you can leave that on. That's how we saw those pictures of Andromeda, of even the most farthest galaxies. We leave the exposure on. Even if you take an exposure on a camera without a telescope and point it at the sky, it's going to make these things called star trails. So this is if you just left that exposure on all night long. This is how those stars would actually move across. All the stars move across our sky. They except for one. The one that doesn't is Polaris. Polaris is right above our axis of rotation, so it doesn't move in the night sky. That is people have used that for centuries, not just centuries, for thousands of years, for navigation, because even the sun, we say the sun rises in the east and sets in the west, but that's only on a couple of days a year that we'll learn about, called the equinoxes. Sometimes it's a little bit north of the east. Sometimes it's a little bit south of east. If your chart back in the day was made in the wintertime and you're trying to use it in the summertime, the sun's going to be in the wrong place. When you're navigating, you're going to be you might be going the wrong way. But Polaris doesn't. Polaris doesn't change. So it's been used as a navigational point for thousands and thousands of years. If you're lost in the woods, you can actually learn how to find Polaris. It'll tell you which way is north. You all probably can't do this. The Little Dipper is a constellation. It's dimmer than the Big Dipper. If you're able to see the Little Dipper, you can. It's the tail. It's the last star in the string in the tail of the Little Dipper is Polaris. What's a lot easier to see is the Big Dipper. The Big Dipper, you can find the Big Dipper. You can find the two stars in the ladle and kind of draw an imaginary line to them, and they will actually point towards Polaris. So you can figure out where Polaris is in your sky. That's actually your discussion question 2 this week. Is to go out and find Polaris. You might want to take a look at that, because you don't wait for that one to Saturday night and then have it be cloudy out. So take a look at that question. It may take you a couple of nights to actually be clear enough to go out and find it. That'll tell you what direction north is. It'll actually tell you what latitude you're at, for those of you who don't know. So if you get kidnapped, not only can you figure out how to get out of the woods by following Polaris the north direction, you can tell what part of the world you're in. Maybe they took you to Siberia, and the Big Dipper will be pointing to a star much further up in the sky. Or maybe they took you to the equator, and Polaris will be down on the horizon. The further south you are, you guys, Polaris is a lot higher in our sky in Chicago than it is in yours. But you can still see it. Here's just another cool star trail. These how the stars move during one night. The stars also move in the course of a season. So let's go back to our Big Dipper. We said, I didn't mention that. It's on this picture. Let's go back. If this is the Big Dipper, if you go out 2 hours later, it'll be down here. It's kind of rotating around. Everything's rotating around Polaris. And after 6 hours, it'll be here. That trick I showed you is going to work the same no matter what. You can still line up those stars, and they'll always point towards Polaris. But let's say we go out at 10 o'clock at night. Now in the wintertime, this is what the Big Dipper is going to look like. Hint, hint. You're used to looking at the Big Dipper. If you've ever looked at the Big Dipper before, you probably think it looks something like these two, because that's usually when you're out, when it's warm enough for you to be out looking at that. When you go, well, never mind. It's always warm for you all. I'm speaking like a Chicagoan. We're used to seeing it there, but it looks different depending on what season of the year it is. It's going to look like that now. In the springtime, it'll look like that. And in the winter and the fall, it'll have a different orientation. Again, the only object in our sky that does not change its position, whether it's the course of the night or the course of the season, is Polaris. Fun fact, it actually will change, but it changes on a scale of thousands of years. The North Star for the ancient Egyptians was a completely different star, because the Earth, I said that tilt doesn't change over the course of one orbit, and it doesn't. But over the course of thousands of years, the tilt actually kind of flops back and forth. It's called precession. And so that changes, it pointing at a different star. So that changes over the course of history, but not over the course of your lifetime. It'll always be the North Star. We have to go back to the ancient Egyptians before we have a mention of a North Star being a different thing besides Polaris. I told you we would talk for 1 minute about the zodiac, and here it is. The zodiac was important to ancient astronomers because most of those stars we can see, like the Big Dipper, is always in our sky. But the ones that are closer to the horizon, meaning closer to the sun, we can't see sometimes, because the light from the sun actually restricts our view. Not that the sun is that big, but because it's so bright. So for instance, right now we're in January. So here's where we are. Daylight here. We can't see Taurus. We can't see Gemini. We can't see Leo because the sun's in the way. Not that it's blocking the light by its surface like it is with the Earth in a scene, but because it's so bright. It's like looking at a firefly next to one of those giant movie premiere spotlights. You're never going to see the fireflies. The stars and the moon are in our sky all the time. You just can't see them because the sun is so bright. So that's what's special about these. They kind of come and go with the seasons. They're always in the sky, but we can only see them during the seasons. good news, good information if you want to plant crops and things like that. The sun's motion in the sky is more complicated as well. It has a seasonal motion, not just east to west, but it is sometimes it's much higher in the sky. In the summertime, actually, it's much higher in our sky than it is in the wintertime. This is an exposure that was taken at 3 p.m. Every 10 days, and you can see the sun is in a different position then. It's called analemma is that shape. It's just a little trivia. You're not going to be tested on that. You will be tested. You do need to understand this. One of the things that you hopefully know about the seasons is that they're different in the northern and the southern hemisphere. Another thing you probably also know about the seasons, we said that the sun is higher in the sky in the summertime than the winter. Maybe you knew that, maybe you didn't. But you probably knew that the days are longer in the summer than they are in the winter. And so we can see that on this images. It kind of tells us that the path of the sun across our sky. In the northern hemisphere, here is it's a special day called the winter solstice, affectionately known as the first day of winter. It's actually the shortest day of the year. The sun is low and it never gets very high in the sky, and it's low in the northern hemisphere. But if we imagine what this looks like in the southern hemisphere down here, you'll see that their daylight is much. There's their daylight. They get so when it's winter in the north, it's summer in the south. When there are short days in the north, there are long days. So day meaning daylight, not it's always 24 hours, but when there's a short number of daylight hours, in the north there's a long number of daylight hours in the south. And the exact same opposite over here. It's summertime in the north. We have long periods of day of sunshine. In the south, they have short periods of sunshine. That is the summer solstice. And then there's 2 days called the equinoxes, where first day of spring, first day of fall, where the length of the days are the same, 12 hours of daylight, 12 hours of night, and the sky is the sun's about halfway up in the sky. All right, and so here is that explanation for the seasons. Sometimes I ask my students, my on-the-ground students, so to speak, in my live classes that, not that you aren't alive, but when I'm talking to them face-to-face, let's call it face-to-face, because on the ground is kind of silly for an astronomy class. We'll say my face-to-face classes, I ask them, what's the cause of the seasons? And some of them know, but some of them say, well, it's because in the wintertime, we're further away from the sun. And that is actually a reasonable hypothesis. Makes sense. If you've got a space heater, the closer you are to it, the warmer you'll be. The further away you get, the colder you'll be. But that doesn't explain that first important fact, that the observation that the seasons are different between the northern and southern hemisphere. So that can't be the cause of. That's not why it's warmer in the summertime. And in fact, another way to disprove that hypothesis is that the Earth is we're actually at the closest point to the moon right now. For those of you, many of you heard about not the moon, the sun. You heard about the eclipse being a supermoon. That's because the moon was closer to the Earth right now. So neither of the orbits of the Earth around the sun or the orbit of the moon around the Earth are perfect circles. And actually, the Earth around the sun is closer to a perfect circle than the orbit of the moon is. So that's not why it gets warmer. Part of the reason why it's warmer in the sun is because the length of the day is longer, as you can see on this plot. let's look at summertime in the northern hemisphere. Notice here's the tilt. We are spinning this way. We're not spinning around this way. We're actually spinning around that tilt. We're going this way. So look how much more daylight we have than night. Right. So the length of the day, the daylight hours is longer here. But in the southern, it's exactly the opposite. So that's one of the reasons why it's warmer in the summer. The other is, you can kind of see on this spot, let me blow it up a little bit. Oops. Notice here, this is summer in the north. The light that's hitting it is much more intense than it is in the southern hemisphere. That is the angle of the sun that it hits the earth is different. Watch, there's a video on it that kind of does an animation that shows you the intensity of the light being more intense in the summertime than it is in the winter. So that's the cause of the seasons in a nutshell. It has to do with the tilt of the earth. If there was no tilt, there would be no seasons. Yes, there would be a slight, it would be slightly cooler out when we were further away from the sun, but the sun is, it's on, the deviations from it being a perfect circle are very, very tiny with respect to how far away it is. So if there was no tilt, the Earth would have the same temperature all the time. Another interesting thing about that daylight, if you go back to that picture and look at the North Pole, for instance, especially on the first day of summer, the longest day of the year, the sun actually never sets. Never sets. Even during the summer season, the sun is only actually going below the horizon on the North Pole for a couple of hours a year. Even now, nobody lives on the North Pole. Not even Santa Claus. The actual North Pole is a bunch of sea ice. There's not even any land underneath there. But people who live in Alaska, they have to worry about, they have seasonal ailments due to having either too much sunlight during the summertime and too little sunlight during the winter. It's not clear. It depends on who you talk to. They're both kind of bad. They both will drive you crazy, and they both will affect you, your vitamins and things in your body. All right. So you can play around this. This you can actually on my lecture slides. You can click on. It's not going to work for us here, but you can click on it. It'll take you to this, and this will do this for yourself. If you do not understand the seasons, it'll show you the directness of the light. You can switch this to a different mode where it'll show you how much energy one of these columns of light during the summertime. The spot that it has to warm up is much smaller than during the wintertime because of that angle. And so you get more intense light that way. Here's what I was talking to you about, the precession. That in 5,000 years, our North Star will not be Polaris, it'll be Cepheus. And if you don't believe me, where is it? If you go back to the ancient Egyptians and look at, they wrote down their North Star was called Dubin. Kind of cool. Their North Star wasn't a dipper. It was in a dragon constellation. It was the third star from the tail of their dragon called Draco. But in another 26,000 years, it'll be back to Polaris again. Again, that's think of the precession. It is like a top that wobbles. When a top is spinning very fast, you don't notice it, but it's actually moving. But as it slows down, you can actually see it moving back and forth. That wobbling is called precession. It's going on the Earth right now. As it, not that it's, I mean, it actually is slowing down, FYI. But there's a thing called a leap second. You've heard of a leap year? There's a leap second. The rotation of the Earth is slowing down because of the effects of the moon. This is actually some kind of popular pseudoscience that you'll hear on Facebook and YouTube a lot. That you're going to hear that that the moon is moving away from the Earth and that the Earth is slowing down. And both of those are in fact true. But the Earth is slowing down 1 second. I think it's every 2 years. And it's moving a centimeter of the 384,000 kilometers away from the Earth it already is. It moves about a centimeter away a year. So nothing to worry about, like they say. Now, in a billion years, that will have some effects that we'll actually talk about. The phases of the moon. Again, the phases of the moon, we're going to study in your virtual lab, so I'm not going to go through it. It's better for you to do it yourself, but you'll see. You can watch this video on our page. You can kind of give you a gist of it. You can also do a demonstration yourself, and I highly recommend you do that. It's outlined in your lab. You just take an orange and jam a pencil in it, and just have one light in the room and kind of move around, and you'll see the phases of the moon on your little orange or whatever. So all of that is caused by the relationship between the Earth and the moon and the sun together. Depending on, I think I got a couple on here. So depending on where it is in this orbit, we see a little bit different part. The key to understanding this, again, is that wall of light. Is that the part of the moon is this is a crescent phase of the moon. That's not the only part of the moon that's lit up. 1/2 of the moon is always lit up, and it's the dark side. Pink Floyd talked about the dark side of the moon. That's not the same thing as I was talking about the far side of the moon. It's just as bright and dark, depending on there's no real dark side to the moon. The moon is always half lit, and that the half that's lit changes depending on where it is in orbit. You'll play around and you'll figure that out. But that is, here's kind of a starting point to that. Notice that no matter where the moon is in its orbit, this is the part that looks like it's lit up. Again, like the giant wall of light. And then you have to put yourself on the Earth and look at what it looks like over here. So the easiest one to visualize without that is picture yourselves on the Earth here. Remember the Earth spins counterclockwise. The moon actually orbits counterclockwise and spins counterclockwise, and the sun spins counterclockwise or orbits counterclockwise around the sun, and the sun spins on its own axis counterclockwise. In fact, 97% of all of the objects in the solar system, in their orbits and their own rotations, are counterclockwise. We're going to learn why that is, and then we'll also learn about the exceptions. Tells us a lot about how the solar system formed. So this is what it looks like from outer space. I showed you. You have to put yourself on the Earth, looking at the moon, and that will give you the different phases of the moon. So this kind of explains why the moon looks different. And remember, this is 27 days ago across here, and again, we usually can only see the moon at the nighttime. So we usually these phases of the moon are harder for us to see. In fact, the new moon is almost impossible to see because it comes up right as the sun rises, and it sets right as the sun sets. And so the sun is so bright, it's hard to see. you have to kind of, if you really want to see this, and in our project, if you can get an image of it, you can get 2 extra credit points. But I've never had a student do it. But hey, you guys, you are probably better than with cameras than my other students. But it's very difficult. You got like 10 minutes after the sun goes down. I would, the only time I've ever seen it is on a beach, right when the sun goes down, or as close. You can see the new moon, and you got about 10 minutes to do it. And actually, when you can see the new moon, it's kind of like what we saw with the eclipse. For those of you who saw the eclipse, that red part is well, that's not true. What you're seeing on a new moon is actually what's called earthshine. It's actually not. It's not light that's actually being reflected directly from the sun. Remember, all of this light we talked about last week. All of this light from the moon, it doesn't have its own energy source. That's the sun's light that's being reflected from it. So the new moon, you can actually see a process that's called earthshine. It's actually light that is being reflected off of the earth onto the moon, and then back from the moon to our eyes. It's called earthshine. So the moon appears even more ghostly than it did the other night during the eclipse. You can barely see it's there. It is I wouldn't say religious, but maybe no, could be religious to some of us. It is mystical. There's lots of people go on quests to try to see this. I've seen it once. It was spectacular. It was moving. That ghost moon, a beautiful sunset, and then a kind of a ghost moon that sets a couple of minutes afterwards. Spectacular. But you're also these crescent phases. When you think of the moon, you generally draw the full moon, and that's because the full moon is up all night long, and it's exactly the opposite of the sun. So when the sun sets, the full moon starts to rise. It's up all night long. It's at the highest point in the sky at midnight, and then it sets right in the morning time. So that's the phase of the moon you're most familiar with. These gibbous phases, where they're mostly illuminated, there's only a sliver missing, they're usually at night. And then these quarter moons, which are these are kind of my favorite. There's 2 phases of the moon where it is actually just, it's ridiculously how amazingly cut in half it is. And then the crescents. The crescents moons are hard to see, especially as they get thinner and thinner. These really thin crescents. You can only see them really, really early in the morning or right at dusk. But your goal for your phase of the moon project, you need to capture all of these. Not this one. That's extra credit. You either need to photograph them or take a sketch of them and write all the information down on there. And you should get started on that project right now. This thing takes, these phases are a month. That's how we define a month. So you got 3 shots at most. Some of these you only have 2 shots at getting. Now, for some of these, there's a couple of these phases that only happen on a particular night. Like the first quarter moon and the third quarter moon and the full moon are only once a month, whereas these phases, you've got the rest in between. So these are easier to get. But you still can't wait till the last minute. If you wait till the last night, you're only going to get 1 phase. If you wait for the last week, you're only going to get maybe 2 phases. Get started on this now. More on that to come. Okay. You'll catch the gist of that is that not only does the the moon look differently, but it rises and sets at different times of the night. And you're going to figure all about that. And it's different in the northern and the southern anyway. There are a couple of really cool videos to watch to kind of help you explain it. So read it in your book. I gave you the gist of it here. Watch those videos and then go and actually see those phases for yourself. This is an important part of this this class is you to figure out how the moon works. And it also works with eclipses. We saw that many people are under the false impression. One of the misconceptions of the phases of the moon is that it's the Earth's shadow. You're going to learn that it's not the Earth's shadow. It's just the perspective. What we saw the other day or other night was the Earth's shadow. That eclipse was the Earth actually getting in the way of the light from the sun. You may say, well, why didn't that happen every month? And that's a very good question. And by everything you had done, if you started it, would kind of give you that impression. But the moon is a little bit tilted. So usually the moon is above the direct line between the sun and the Earth, or below it. But every now and then, twice a year, they're actually in the same plane. And if that twice a year actually corresponds to either a new moon or a full moon, we get what's called an eclipse. If it's a new moon, it's actually a solar eclipse. It's the moon that's blocking the light from the sun. If it was as the other night, it is the Earth that's blocking the light from the sun. So we have two kinds of eclipses, and they only happen a couple of times a year. It's called an eclipse season. The solar eclipses have mystified humans from the beginning. And they still do. They're amazing things to do. The last one, we had one 2 summers ago in North America that it was just amazing. I don't know if you saw it or not, that it's there. It gets dark during the day for a couple of hours. The moon is actually getting in the way. Now, you can see the moon is small relative to the Earth. This is what it is in actual distance, as we saw. But if I kind of, to get a better idea, check it out. And if you actually watch that video, that epic video of the Earth rotating, there's a portion of that. Go back, you can actually see the shadow of the moon go across the Earth. It's only darkens a tiny spot on the Earth. So these are much harder to see. They happen once or twice a year, but you have to be at exactly the right spot to actually be able to observe that shadow. And if you want, this slide actually shows you when to go. We got to wait till 2024 if you want to wait in North America. But there's one about every year. They're not all total, but there's at least a partial every year. And people, they have cruises if you want to go see one. And go check one out. Don't wait till 2024. Go schedule your next. Look at this one. Go down. Where's 10? 10's in 12. That one's further away. 2018. Go do this one. Go down here in Chile. Go see the eclipse. I'll be there. Mostly, not just to see the eclipse, but because one of the greatest observatories. As my real girlfriend says, my other girlfriend's called Alma. Is actually an observatory down here in Chile. Amazing place. We'll show you lots of pictures from there. It was actually the telescope from that first slide I showed you in the introduction. Okay. So solar eclipses block the light from the moon, blocks the light from the sun. An amazing coincidence that when the moon is in its closest when it's in its closest orbit around the Earth, its size is almost exactly the size. The apparent size is almost exactly this apparent size of the sun. Now, be careful doing this. You do not look at the sun. But if you do have your solar eclipse glasses left over from the other from a couple years ago. You can look at the sun safely with them now, but you'll notice that the ring that it makes is about the same ring as what you see for the moon. And so if the moon is in its closest place, we get what's called a total eclipse. If not, we get what's called an annular, which is almost even cooler, because you get like this ring. And then sometimes they don't really line up, and so it just looks like there's a little piece being eaten out of. This is a total eclipse. This white stuff here, it's still light, and this you can actually observe with your naked eye. And this is when it gets dark and the animals come out. This is the atmosphere of the sun. You can actually see that with your own eyes. It's the only time you can actually see that with your own eyes without a filter. It's called the corona. It's very special. We use eclipses. We either make them artificially with our telescopes devices, or we actually wait, once a year to actually make measurements. So not only do tourists follow, or astrotourists follow eclipses around, but scientists follow them around. Scientists will be going down to see the next total eclipse to make scientific measurements of the atmosphere of the sun, because this is too bright. It normally just washes that out, even with our best solar telescopes. Here's like a time lapse of that eclipse that was taken a couple of summers ago, and it literally did. It got dark for 8 minutes. You can see stars. We're going to learn next week. This was the first proof of Einstein's theory of relativity was during an eclipse. Apparently, it pissed off the pigeons in wherever it was. It wasn't. I guess it was in Paris a couple of years ago. They got mad. They're not used to it getting dark during the day. Okay, the rest of this are just some pretty pictures of these objects. And then this is what we saw the other night. The lunar eclipse is kind of the opposite. Now the Earth is blocking the light from the sun. The Earth is a lot bigger than the moon, so it doesn't matter where you are on the Earth. Well, it does. You got a 50% chance. It just has to be at night in order for you to see the eclipse. So we were lucky. It was in North America this time, and we got to see the whole thing. These are much because of that. We get one of these every year that we can actually see. It's just a matter of twice a year sometimes. You just gotta be in the right time. Okay. Here is why was the moon red the other night? It's because of our atmosphere. It's the same reason why the sunsets are red. When light goes through our atmosphere, it interacts with the air particles and it gets bent. And like a prism or a rainbow, the colors get bent in different directions. The red light gets bent the most. The red light is actually what, so the light from the sun comes in, goes through our atmosphere, gets bent to where it actually hits the moon, yes, believe it or not, and then bounces back. Remember, light, that's an incredible distance, 384,000 kilometers away, but it only takes it a second. And that's how fast light is. So light from the sun goes through our atmosphere. What you were seeing, if you did see this, that red moon, that blood moon, was the light you were seeing came from the sun. 8 minutes, takes 8 minutes from a photon from the remember the particle associated with light is called a photon. That photon left the surface of the sun, traveled through 93 million miles in 8 minutes, went through our atmosphere in a fraction, thousandth of a second, but it got bent. It hit a particle of air and got bent, kind of just like a pool ball. Only light is weird. The red pool balls get bent differently than the blue ones do. So it got bent. Traveled hundreds of thousands of miles in a second, bounced off the surface of the moon and bounced back to your eye, that's what you were seeing. That's amazing to me. I don't know about to you. That's one of the that's thinking things like that is why I became an astronomer. Why I love astronomy. Just the craziness of all of that. And we're going to learn. This is kind of we're going to learn why this gets bent, how our eyes work, why this gets reflected. We're going to learn how the moon formed, why it's so close, why it's so big. It turns out, in our sampling of all of the other moons of our solar system and all the moons of other systems, we got a giant moon, relatively speaking. And we're going to learn in this class that if it wasn't for the moon, we wouldn't be. I mean, there might be life on Earth, but it wouldn't be us. We wouldn't have any. We wouldn't have oceans if it weren't for the moon. Think about that for a while. I'm not going to give away every secret for this class. Okay, so there weren't any of these, and I'm not going to go through these, but these are kind of like warm-up quizzes. So before you take the quiz this weekend, look through my PDFs, and they have they're like mini quizzes. They ask you a question, and then they'll tell you the right answer. Just kind of a practice quiz, another way for you to make sure you understand what's going on. Okay, that's it for this section for tonight. I am going to take a little break. Unfortunately, we had to do 2 chapters. I'm going to take a little bit of a break, and then we're going to get started on the history of astronomy, one of my favorite chapters. Let's have a 15-minute break, and then we'll come back. All right. Thank you.